Hello and welcome to our second lecture of the week. And today we finally get to start Chapter 5. Chapter 4 was a pretty long one, and actually Chapter 5, as it turns out, is fairly short. So we won't be on this one too long. I'll have the homework problems listed for you soon, and be sure to get right on those because, as I said, it's not a very long chapter, so we probably won't be spending very long on it. The topic of the chapter is thermochemistry. And from the word thermo, you might glean that it has something to do with heat, and indeed it does. Thermochemistry is the area of chemistry that deals with the role played by energy in chemical reactions, and that energy, in many cases, takes the form of heat. It can also take the form of light or electricity or even some other things sometimes, but more often than not, it'll be the energy will be present in the form of heat. As it turns out, all chemical reactions require, or all chemical reactions involve energy in one way or another. Most reactions will take in a certain amount of energy because, in order for a chemical process or a chemical reaction to occur, the bonds among the reactant molecules have to be broken before anything else can happen. And in order to break the bonds in those reactant compounds, you have to put energy in. And then the atoms rearrange themselves and they come back together in different combinations and form new bonds. And when you form new bonds, you get energy out. And so really, essentially, every chemical reaction involves putting in some energy and taking out or getting out some energy. The major distinction between the types of chemical reactions will be based on whether the amount of energy that you have to put in to break the bonds is greater than or less than the amount of energy you get out once new bonds are formed. That's the major distinction that's made in thermochemistry between types of chemical reactions. So in other words, if the reaction basically takes in more energy to break bonds than it releases when new bonds are formed, that will be known as an endothermic reaction because the reaction has taken in energy overall. So it's basically taken in a lot of energy in order to break the bonds of the reactants. And when the new bonds and the products are formed, you get out a little bit of energy. So the net amount of energy released is this much. But still, it's energy that's being released, not absorbed. So if the energy input to break the bonds is greater than the energy released when new bonds are formed, the reaction absorbs energy overall. Okay, let's say absorbs. And that's known as endothermic. On the other hand, it could be the other way around. If the energy released when the new bonds are formed is greater than the energy you have to put in to break the bonds in the reactants, then the reaction releases energy, and the net amount would just be the total amount released minus what you have to put in, and but it would still be a net amount of energy that's being released. And that would be known as an exothermic reaction. Exo as in exiting. The heat or energy is exiting from the reactant molecules. So it's giving off energy. In nature, lower energy tends to be associated with greater stability, and nature tends to favor greater stability. So things in general just tend to lose energy over time to the surroundings, to the environment, whatever. And so exothermic reactions, that is reactions where the reactants have a lot of energy stored up in their bonds and the products have much less energy stored up in their bonds. Exothermic reactions tend to be spontaneous because they're going in the direction that nature wants them to go. They're going from high energy to lower energy, and that's accompanied by a release of the excess energy to the environment. Endothermic reactions are usually not spontaneous. And that's because you're trying to basically go against nature. You're trying to go from a low energy situation to a high energy situation. And in order to do that, you essentially need to keep putting energy in from outside, or the reaction will stop. And that's what we mean by non-spontaneous. It won't happen on its own. Reactions, chemical reactions involving energy changes are really all around us. We run our bodies on chemical reactions that produce more energy than they take in. That's how we manage to, sit upright and walk around and breathe and things like that. Society runs on things like combustion of fossil fuels. Obviously, when we burn fossil fuels, we put a little bit of energy in to break the bonds and the reactants, and then we get a lot of energy out along with the products. On the other hand, if we want to move to cleaner energy than fossil fuels by burning hydrogen, say, instead of fossil fuels, well, one way you can get hydrogen is by electrolysis of water. That is, you take some water, pump quite a bit of electricity into it, and you can actually break the H2O molecules up into hydrogen and oxygen separately. And then you can burn the hydrogen for energy. But in this case, the energy that you have to put in is much greater than the energy you get out when the hydrogen and oxygen are produced. So essentially, in an exothermic reaction, energy is essentially a product. I mean, there's a little bit of energy going in, but there's a whole lot of energy coming out. And so, in effect, the energy going in is canceled out and then some by the energy released. And so you only write energy on the product side. And in something like electrolysis of water, this is propane, by the way, this is the equation for burning propane, and you get quite a bit of energy out as product. For something like the electrolysis of water, which is endothermic just means that energy is going to be effectively a reactant in the reaction. So you have to put energy in and keep putting it in to get the reaction to occur. So the water plus energy in the form of electricity will yield hydrogen and oxygen as two separate elements. Okay, we as chemists, we're more interested in the molecules, the reactants, and the products. And so we don't usually write in the word energy. But for illustration purposes, in this chapter, we often will write in the energy, just to show you where it is. Now, of course, in this reaction, the electrolysis of water, you get out some energy when the hydrogen bonds in H2 are formed, and when the O bonds in oxygen are formed, but you don't get out as much as you have to put in. And so again, the energy released in this case is canceled out and then some by the energy that you have to put in. All right, so that's sort of an introduction. And to go into some more detail on the introductory stuff, the first section is titled Energy Basics. The numbers over here are the page numbers, 232 in the hard copy and 242 in the PDF. This is where we start sort of at the very basis of thermochemistry. We'll start at the very beginning and define energy. Energy is defined in physics as the ability to do work or to supply heat. And that kind of begs the question, what's work? Work is the ability to move matter against an opposing force. And in physics, if you've taken physics, or if you're going to take physics, you will see it. Work is equal to force times distance. So you push with a certain force for a certain distance, and you've done work. Okay. There are different types of energy, and there are actually different ways of categorizing energy. But the main types that we usually consider are potential energy and kinetic energy. Within potential energy and kinetic energy, there are various subtypes also, which we'll get to later. But for right now, potential energy we'll define as energy that something has because of its position or condition or its composition. That is, where is it or what is it made of? Okay. Potential energy is stored energy. That's why we call it potential energy, because it has the potential to do work, but it's not actually doing work right now. So it's stored energy. It's not being expressed, but it could be potentially. Some examples of potential energy would be the energy stored in chemical bonds. So chemical energy is a form of potential energy. And also the energy something has due to its height above the Earth. That's called gravitational potential energy. So if I take this pencil and I raise it up to this height here, as you can tell, it's pretty close to the camera, it has a certain amount of potential energy. If I put it down here, it has less potential energy because it's lower relative to the surface of the Earth. And so that is energy that's based on its position. Kinetic energy, on the other hand, is energy that has to do with movement. And there are various types of movement that can qualify as kinetic energy. One example would be the vibrational energy that molecules in a solid have. So even though, remember, even though molecules in a solid to us usually appear like they're not moving, like the molecules in the binder here, looks like they're not moving. But if we were able to see on a small enough level, we would be able to tell that the individual atoms and molecules that make up this substance actually are vibrating in place. They can't move around or past one another, but they can vibrate in place. And that's because of the thermal energy that's present in the environment. And the only way you can get that vibration to stop is if you were to cool things down to absolute zero, which nobody has ever actually managed to do. So there will always be some thermal energy and some vibration of particles in not just solids, but any substance. Even if you were, like 0.0001 degree Kelvin, that's 0.0001 degree above absolute zero, those molecules would still be vibrating at least a little bit. And then the higher the temperature gets, the more thermal energy there is, and the faster the molecules will vibrate. Other types of kinetic energy would be the translational energy that you have when molecules move around and past one another. Like, for instance, in a gas, since there's essentially no attraction between gas particles, they're able to zip around and past one another at a high rate of speed. And so they actually have very high kinetic energy because they're moving very, very fast. Also qualifies as kinetic energy would be electrical energy. The flow of electrons through a wire is movement, and so that qualifies as kinetic energy also. Whenever we're dealing with energy, an important concept that we always have to obey is conservation of energy. Got to obey it because it's the law of conservation of energy. It's similar to the law of conservation of matter, in that for conservation of energy, the law goes to the effect that the total amount of energy in the universe is constant. Okay. So it doesn't increase or decrease over time, but it can be converted from one form to another, or it can be transferred from one place to another, but it cannot be created or destroyed. Okay. So the total energy present in any isolated situation has to remain the same. If you think of an object falling, as I mentioned before, if I take this pen and put it up here right near the camera, it's as high as it can get for you to still be able to see it. And it has a certain kinetic energy related to its height above the ground. If I allow it to drop, it now has a lower kinetic energy than it did before. And the difference between kinetic energy it had up here and the kinetic energy it has down here is equal to the potential, the difference between the potential energy it had up here and the potential energy it has down here is equal to the kinetic energy that it had while it was moving from one place to the other. So if we look at, say, the initial potential energy when it was up here, that becomes kinetic energy while it's falling, and then that becomes the final potential energy once it's resting on the table again. Well, the fact is that the initial potential energy is the greatest energy here, and that is equal to the final potential energy plus the kinetic energy that it had while it was moving. And so these two sides are equal. Energy has been conserved. The amount of energy at the end of the process is the same as the total amount of energy at the beginning, and the law of conservation of energy is satisfied. Sorry. All right, so to move on to some deeper definitions here, things like thermal energy and temperature and heat and how they relate to each other. This is on page 234 in the hard copy or 244 in the PDF. Thermal energy is just the kinetic energy from the random motions of the particles in a sample or a substance. And that would include, if it's a solid, then it would be mostly made up of just vibrations. If it's a liquid or a gas, then it would be a combination of the vibrations of the molecules and also the translational energy of them moving around each other. But all of that's kinetic energy because it all involves movement. Temperature is just a way to measure the average kinetic energy of the particles in an object or a sample. So thermal energy is the actual energy of movement. Temperature is a way of measuring that kinetic energy, and it's the average kinetic energy of the particles in an object. If you look at the atoms in something like, well, say this pen, if you look at the individual atoms or molecules in the pen, there will actually be a range of kinetic energies. Some of them are vibrating really fast, some of them are vibrating more slowly. And if you were to average together all of those kinetic energies of all of those molecules in the pen and then measure it, what you would end up with is the temperature. We get the average kinetic energy of the particles in an object or a sample because, well, our temperature probes are too big to get the kinetic energy of any one molecule. Molecules are really small. And so if there's a rapid vibration of the molecules, that means there's a large amount of thermal energy present, and that gives you a large average kinetic energy, and we say that the object is hot. And I just noticed that the way I wrote Ke looks like ice. No, it's Ke. If the vibrations of the particles are slow, that would be equivalent to a low amount of thermal energy, or a small average kinetic energy, in other words, and that we would term as being cold. So hot means fast vibrations, cold means slow vibrations. And if you increase the thermal energy, you end up increasing the temperature. Sometimes that doesn't happen if there's a phase change involved. So if increasing the temperature causes the solid to melt, then that can mess things up a little. But within a given phase of matter anyway, the increasing thermal energy usually increases the temperature. Now, of course, we're interested in measuring temperature, which we normally do with things like thermometers. And the principle of the thermometer is based simply on the fact that most substances increase or expand when they get warmer and contract when they get colder. And different substances will expand or contract at different rates. Some substances expand a lot when they get warmer and contract a lot when they get colder, like, for instance, gases. Gases have huge changes in volume with even small changes in temperature. And on the other hand, some things only expand a little bit when they warm up and only contract a little bit when they get colder. For instance, most solids, and liquids would be somewhere in between. Sometimes even things like railroad tracks can expand quite a bit when they get hot. When they lay out railroad tracks, they normally leave a space between the rails, and that allows for expansion and contraction as temperatures change in the air. And that's what causes the clickety-clack sound that you hear when you're riding on a train. It's the wheels in the train going over those gaps between the rails. But sometimes when there's a really bad heat wave, like we have in places like Texas and Arizona and Southern California every summer, where the temperature will get up in the range of 110 or 120 degrees for days on end, and also seems to happen in Australia their summer, which is our winter. The steel rails can expand so much that they actually touch each other. And once they touch each other, they start bowing outward, and they basically have to shut down the rail line until the rails can be replaced. Because if a train tries to roll over something like that, it's going to derail. So even something like that, like steel, can expand significantly if the temperature increases enough. What we actually use in practice would be something like, say, mercury. Mercury, when placed in a glass tube, will expand as it gets warmer. So the column of mercury gets higher as the temperature goes up, and it contracts as things cool down, or in other words, the height of the column of mercury goes down as it gets cooler. And this works well because mercury is a liquid, and it also expands and contracts a relatively large amount for changes in temperature. The thermometers that have a silver liquid inside them, those are the ones with mercury inside them. They're not used so much anymore because, of course, mercury is toxic. So if you drop the thermometer, you got a problem. Most thermometers involving liquid today are filled with alcohol, and those would be the ones that are colored. So basically, if the liquid inside the thermometer is red or green or blue or some other color, then it's most likely alcohol. An alcohol thermometer would be one. Actually, I've got it upside down, haven't I? I don't know why they used a fish skeleton on this, but anyway, you'll notice that the liquid inside the thermometer is red, and that means that it's actually alcohol, not mercury. But that's okay, because alcohol also expands and contracts quite a bit as it gets, as it warms up or cools down. And basically what they do is they fill the, they put some alcohol or mercury in the tube, and then they calibrate off, where certain temperatures are. And you can see by the scale, it's a little under, it's just about 70 degrees in here right now. There are also other ways of measuring temperatures. The mercury and alcohol thermometers tend to be only useful within a certain range. And if the temperature gets too high, then the problem is that the alcohol or the mercury will vaporize and turn to a gas. And when that happens, it expands so much that it actually breaks the glass and the thermometer is ruined. So for higher temperatures, we tend to use what's known as a thermocouple, and that's based on the relative expansions of two different metals relative to each other. And that can, basically, you can use that to determine what the temperature is. Okay, heat now is a form of energy. Although technically heat refers to a transfer of energy, the word heat is often used for the thermal energy itself. Okay, so technically heat involves transfer of thermal energy, but in practice we often use it just to mean thermal energy. And thermal energy is transferred from warmer areas to cooler areas. So when we talk about heat flow or energy flow, it always goes from areas of higher energy to areas of lower energy. So you can think of it as like water flows downhill. Well, so does heat, high to low. So it goes from an area of greater thermal energy or a warmer area to an area of lower thermal energy or a cooler area. If the heat flow in a given situation is not controlled, right, that is, if we don't intervene to stop it, then it normally continues until both areas have the same level of thermal energy, or in other words, until they're the same temperature. Because nature tends to favor spreading things out and making things equal and evenly distributed as much as possible. That's why this happens. So if you don't actually stop the heat transfer, it'll keep going until it's spread out evenly and basically everything is the same temperature. And this will happen like if you take a hot piece of metal and drop it into cold water, the metal will cool down and the water will warm up because the heat is, or the metal is transferring heat from itself to the water because the metal's hotter and the water's colder. And that process will go on until the metal and the water are at the same temperature. And at that point, there's no gradient in thermal energy. So there's no impetus for transferring energy. And they just stay that way. Let's see, chemical or physical processes, for that matter, can release or absorb heat or energy overall. And again, if the process releases heat overall, that is net, then it's called exothermic. And if the process absorbs heat overall, then it's known as endothermic. And before we get into the measurement of heat, I think I'm going to stop there for the first segment, and we'll start the next segment in just a moment.